Imagine this. A massive wave of charged particles is hurtling through space, heading straight for Earth. This isn't science fiction. It's a solar flare, and it has the power to disrupt everything from your GPS to the internet. During periods of high solar activity, these events can occur hundreds of times in a single month. So, how do we prepare for something so unpredictable? Enter Surya, a groundbreaking AI model designed to decode the sun's mysteries and protect us from its most violent outbursts. But here's where it gets controversial. Can an AI truly predict the chaos brewing 93 million miles away? Let's dive in. For over 15 years, NASA's Solar Dynamics Observatory, SDO, satellite has been tirelessly observing the sun, capturing an endless stream of data about its behavior. But there's a catch. When SDO launched, artificial intelligence was still in its infancy, and tools to fully analyze the satellite's trove of imagery were limited. Fast forward to today, and scientists at IBM, NASA, and 8 other research centers have developed Surya, a first-of-its-kind foundation model for solar physics. Named after the Sanskrit word for sun, Surya leverages raw data from SDO to predict dangerous solar storms that could endanger astronauts, satellites, and even life on Earth. Why does this matter? Picture this. A solar flare erupts, and it takes just 8 minutes for its light to reach us. However, the harmful particles it releases may take hours or even days to arrive. This lag time means scientists must predict these storms far in advance to mitigate their impact. We want to give Earth the longest lead time possible, explains Andres Munoz Jaramillo, a solar physicist at the Southwest Research Institute and one of the project's lead scientists. Our hope is that the model has learned all the critical processes behind our star's evolution so we can extract actionable insights. But predicting solar storms isn't as simple as checking the weather forecast. The sun operates on principles of plasma physics that are still poorly understood compared to Earth's atmospheric dynamics. To bridge this knowledge gap, Surya transforms historical SDO data into a digital twin of the sun, a virtual representation that can be customized for various scientific applications. It's part of IBM's broader initiative to use generative and automated approaches to empower algorithms at scale. According to Juan Bernabe Moreno, IBM's director overseeing the collaboration with NASA, with Surya, we've created the first foundation model to look the sun in the eye and forecast its moods. The implications of this breakthrough are staggering. For instance, Kathy Reeves, a solar physicist at the Harvard-Smithsonian Center for Astrophysics, has long awaited such a tool. She envisions using Surya to automate the painstaking process of extracting features and events from petabytes of data. This is an excellent way to realize the potential of this data, she says. Now we can focus on the science instead of getting bogged down in manual analysis. So how does Surya work? SDO captures images of the sun every 12 seconds, but these aren't ordinary snapshots. They're taken across multiple wavelength bands to measure the temperature of the sun's layers. The surface is relatively cool at 5,500 degrees Celsius, while the corona, its outer atmosphere, sizzles at up to 2 million degrees Celsius. Additionally, SDO maps the sun's magnetic activity, revealing sunspots and tracking the twisting of magnetic lines. To train Surya, researchers used 9 years of this data, harmonizing different types before experimenting with AI architectures. They ultimately chose a long-short vision transformer with a spectral gating mechanism, which proved adept at handling SDO's high-resolution 4096 by 4096 pixel images. One of the most exciting aspects of Surya is its ability to predict future solar activity. Unlike previous models that reconstructed missing data, Surya was trained to predict what SDO would observe an hour ahead. In early tests, the model demonstrated a 16% improvement in solar flare classification accuracy, a significant leap forward. Johannes Schmudi, the technical project lead on the IBM side, notes, "It's remarkable that the model performed better when we let it figure out the sun's rotation on its own. Surya also addresses long-standing mysteries, such as why solar winds intensify during the sun's quiet phase and the magnetic structure of the corona. To make the model accessible to non-AI experts, the team developed Surya Bench, a collection of curated datasets and benchmarks tailored for specific tasks. These include predicting active regions, detecting extreme ultraviolet radiation buildup, and forecasting solar wind speeds. Spiros Kasapis, a postdoc at Princeton who contributed to Surya Bench, explains, "These are the regions that produce all the magnetic particles we're interested in. This is essentially the very beginning of our relationship with the sun. As the sun approaches its next solar maximum, a period marked by increased magnetic activity and solar flares, tools like Surya become even more critical. Active regions on the sun's surface grow larger, releasing energy that triggers coronal mass ejections, CMEs. When these interact with Earth's magnetic field, they can disrupt GPS systems, overload transformers, and knock satellites out of orbit. Understanding the sun's behavior is key to safeguarding our technological infrastructure. But here's the question. Can AI models like Surya truly keep pace with the sun's unpredictable nature? Or will unforeseen challenges arise as we rely more heavily on these tools? The team behind Surya believes this is just the beginning, a stepping stone toward deeper discoveries about our closest star. What do you think? Share your thoughts in the comments below.